Welcome to The Explainer. So today we are diving deep into the powerful, and I mean really powerful, connection between calculus and physics. You probably learned them as totally separate subjects, right? Well, we're about to see how they're actually two sides of the same coin, and how together they give us the language to describe reality itself.
So let me just start with a big question. You've sat through the classes, you've probably done more problem sets than you can count. But have you ever really stopped and thought about what you were learning? That it's, and this is no exaggeration, the literal language the universe is written in.
Here's the core idea, the one thing to remember. Physics is the part that asks all the big questions, how do things move? Why do they speed up? How does energy get from here to there? But to actually answer those questions with any kind of precision, well, you need a special language for that. And that language is calculus.
And the perfect place where these two worlds collide is in kinematics, which is just a fancy word for the study of motion. Everything here, and I mean everything, boils down to three key ideas that are totally tangled up with each other: an object's position, its velocity, and its acceleration, all as they change over time.
Okay, let's really get into this with a metaphor that I think is super helpful. I like to call it the motion ladder. This is going to help us really visualize how these concepts, position, velocity, acceleration, are all connected, and how calculus lets us climb up and down between them.
First, let's think about climbing down the ladder. So we're starting way up at the top, with the big picture, right? Like we know the entire path of a car's journey, but our goal is to zoom in and figure out what's happening at one single tiny instant in time.
And how do we do that? We use the derivative. You can think of it like a mathematical magnifying glass. When you take the derivative of the position function, poof, you get the instantaneous velocity. That's literally the speed on the speedometer at that exact split second. And then you do it again. Take the derivative of velocity, and you get acceleration, which is just how quickly that speed is changing. See? It's this beautiful, logical climb down the ladder.
But here's where it gets really cool. This is not a one-way street. We can also climb up the ladder. We can start with just the smallest bits of information, like an object's acceleration at every single moment, and use that to rebuild the entire story of its motion.
For this climb up, we use the opposite tool, the integral. By integrating acceleration over a period of time, we're basically adding up all those little changes in speed to find out the total velocity. Then you integrate the velocity, and you're adding up all the little changes in location to find out where you ended up. Just like that, we've climbed right back to the top.
So the whole point here is this perfect, beautiful symmetry. The derivative is like taking a movie of a car's journey and breaking it down into an infinite number of single snapshots. The integral, that's what lets us take all those individual snapshots and stitch them back together to watch the full movie. One breaks it down, the other builds it back up.
All right, so we've got this amazing toolkit for describing motion. But let's push it a bit further. It turns out this exact same calculus is also what we need to understand the causes of motion, things like forces, and the consequences, like work and energy.
I'm sure you remember this from your first physics class, that nice, simple formula. Work equals force times distance. And look, it's a great starting point, but it's got one huge catch. It only works if the force is perfectly, totally constant. And let's be real, in the actual world, that almost never happens.
So what do you do then? Just think about stretching a spring or a rubber band. The farther you pull it, the harder you have to pull back, right? The force is constantly changing with the distance. So how on earth do you calculate the total work you did? And boom, this is where our calculus toolkit comes in to save the day again. We use an integral. It's the same exact idea as before. Just like we added up all the tiny changes in velocity over time, we can now add up the tiny bits of work done over every single point along the path. It's the only way to get a precise, real-world answer.
And this idea, this powerful concept of using integrals to sum up things that are constantly changing, well, it shows up everywhere in physics. You want to calculate the mass of some weirdly shaped asteroid where the density isn't the same all the way through? You integrate. You need to find the potential energy stored in a gravitational field. That's an integral. Even something like figuring out the work needed to pump all the water out of a swimming pool, you guessed it, it all comes down to the same fundamental tool.
So we have this absolutely amazing mathematical toolkit. But, tools are only useful if you know the rules of the game you're playing. And in physics, those rules are the deep fundamental laws that govern how everything, and I mean everything, in the universe interacts. And this is the absolute bedrock of it all. Newton's three laws. First, you've got inertia. Then, the big one, the famous F equals ma. This is the absolute linchpin. It's the equation that directly connects a physical cause, a force, to its effect, the acceleration we were just calculating with calculus. And finally, action-reaction. These are the non-negotiable rules of the road.
Now, layered on top of Newton's laws are two principles that are so powerful they feel like cheat codes for physics: the conservation of momentum and the conservation of energy. In any closed system, these two things, momentum and energy, can't be created or destroyed. They just move around. This is huge. It means you don't have to track every little detail of, say, a car crash. If you know how much momentum and energy was there before, you know exactly how much is there after. They are the ultimate problem-solving shortcuts.
And what's just, it's mind-blowing, is that every single concept we've talked about for things moving in a straight line has a perfect mirror image for things that are spinning. Mass becomes moment of inertia. Force becomes torque. Momentum becomes angular momentum. The math works exactly the same way, which just shows you how deep and consistent these physical laws really are.
Okay, so we've put all the pieces together. We've got the language of calculus, we've got the rules from physics. So what? What does this actually give you? What is this new superpower? Well, it means you've basically gained a superpower. All of a sudden, calculus isn't just some abstract math class you had to suffer through. You can finally see it for what it truly is. It's the underlying operating system that runs physical reality. You now have the tools not just to describe what you see, but to actually model it and even predict what's going to happen next.
So the big takeaway here is that getting a handle on this synergy between calculus and physics, it's about way more than just passing a class. It's about fundamentally changing the way you see the world around you. It gives you the power to build your very own models of reality. So the only real question left is, now that you have this power, what are you going to model first?